Assalamu alaikum. I am Marina Kashif, and here we are going to start our lecture number 2 of digital and logic designs. For digital and logic design, I am following the book of Floyd, Thomas L. Floyd, a famous writer of digital fundamentals, and here we are studying his 11th edition. Our today's topic of lecture number 2 is ADC, analog to digital converter, 2 DAC, digital to analog converter, sampling. What is sampling? To get discrete signal from continuous signal. In the last lecture, we studied what is signal. Also, we can convert continuous signal to discrete signal. This process is called sampling. Here we start the explanation. Let us take an example of the sound. Here is a graph of the amplitude of sound with respect to time. Now I am plotting few points on this graph like this. Now I am taking these points only and I will get the graph like this. Here you can see that you are getting the information, the lowest point, the maximum, then again lowest point and the maximum of the other side, again minimum and maximum. This is called sampling. Taking another example of the sound, this is a graph of the amplitude of sound with respect to time, but now I am taking points more than the previous like this. Now I am taking out these points only and I can see this. Here you can see you are getting more than last points. Like in this you are getting 2 points, minimum and maximum, but here there is also another value which is the medium one. The data is stored in discrete form in both of this. We have stored the information of our sound in discrete form in both of this. But which one is better? In which the number of points are greater, because it makes it easy to retrace. So maximum information can get. So this is the basic method of sampling. What is the theorem? What is the science between sampling? We will follow the theorem, Nyquist sampling theorem, in which Fs is greater than 2Fm. Now what is Fs? Fs is the sampling frequency in which we are thinking of number of points, and Fm is the fixed frequency of our data. Let's suppose Fm is 50 Hertz, means the amplitude of the sound, the change in sound is per second is 50 Hertz, and sampling frequency is 100 Hertz. This is the minimum relation. Other than that, we will not get maximum information from the graph. As you can see in this graph, let's suppose that it is the Fm. Here is the Fm, the number of lines passing through a single point in 1 second. Let's suppose from this point to this point, the value is 50 Hertz. Our sampling points should be from this to this is 100 Hertz. Only and only then we can get maximum information. So it has been concluded that sample frequency should be greater than, in fact, 2 times the analogous frequency. Now let's start the number systems, a very important or the milestone of DLD, digital logic designs. There are many types of number systems. Here I am mentioning decimal, binary, octal, hexadecimal. We will study it very briefly in our next coming slides, inshallah. So I'll start from the decimal. Being humans, we have 10 fingers, alhamdulillah. And due to this, it becomes very easy for us to understand the decimal system. But in digital system, we need two value system, which is called binary. Because in digital system, in discrete system, there are basically only two values, yes or no, open or closed. Or one finger, if you prefer, you can say it like this. The other systems are octal and hexadecimal systems. They are also very important and very easy to understand other than binary numbers. Binary numbers are basically very difficult to read. Decimal is very easy to read. Being humans, we can only read decimal easily, and octal and hexadecimal as compared to binary becomes very easy to read. Decimal number, the other name is radix 10. Base 10 we can say it base 10, or also we can say it radix 10. Humans use the decimal number systems as a default. So when we see a number, its base or radix is 10. But in our daily life, we have never mentioned F56 bracket on subscript there is 10. We just write it simply 56. Each digit is weighted based on its position in the sequence power of 10. Here the word very important is from the least significant digit power of 0 to the most significant digit highest power. Each digit must be less than 10, that is 0 to 9. Either it is least significant digit or most significant digit, it should be less than 10. For example, here I am taking an example of a number 2375, which is a decimal number, and we are going to evaluate it in terms of least significant digits and most significant digits. Here the number is 2375.46. The most significant digit is 2 and the least significant digit is 6. Now here I'm not mentioning ones, tens, hundreds values. Here I'm mentioning it according to DLD, digital information, like its place is D0, its place is D1, D2 and D3. In D3 there are 3 zeros, 10 raised to power 3. In D2 there are 10 raised to power 2. In D1 there is 10 raised to power 1. In D0 there is 10 raised to power 0. Similarly, after decimal there is D minus 1 means 10 raised to power minus 1, 1 over 10, whose value is uh, 1 by 10. Similarly, 1 by 100. So after multiplying these values, 2 multiplied by 10 raised to power 3, I get 2000. 3 multiplied by 10 raised to power 2, I get 300. 7 multiplied by 10 raised to power 1, I get 70. Similarly, 5 multiplied by 10 raised to power 0 or 5 multiplied by 1, I get 5. 4 divided by 10, I get 0.4, and 6 divided by 100, I get 0.006. In the next step, I'm adding all these numbers and I will get my number 2375.46. So there is the evaluation of this number. Binary number, which is also called radix 2. In digital technology, binary numbers are very important. Basically, our transistor, which is the basic element of integrated circuits, it has binary language on or off because it is a switch. Each digit of the number is called a bit, or which is short for binary digits. An 8-bit group is referred as a byte, and a 4-bit group is referred as a nibble. Each bit is weighted based. Again, this term is very important. Here we are using powers of 2 instead of power of 10. In decimal, we are using powers of 10. Here we are using powers of 2. And the powers are moving from LSB to MSB. Each bit must be less than 2. Similarly, as in decimal, each digit should be less than 10. Here the each digit should be less than 2, and there are only two numbers, 0 and 1. We are going to evaluate 1010.11 here. Let's see the evaluation. This number 8 plus 0 plus 2, and the number is 10.7510. So from this information I get this information. So this is the conversion of binary number to the decimal number. Octal base and hexadecimal base. Listen guys, this is the only introduction of all these number systems. We will see them in very detail in our next lectures. In octal base, we will make the groups of 3, and in hexadecimal we make groups of 4. Whose groups? Groups of our binary information. For example, this is the number 0 111 00 111. If I make group of 3, I will get a number which is octal. And if I make the group of 4, I will get the number which is hexadecimal. In octal, the numbers are always less than 8, means from 0 to 7. And in hexa, the numbers are always less than 16, means from 0 to 15. The numbers after 9 in hexadecimal are like A, B, C. A for 10, B for 11, C for 12, D for 13, E for 14, F for 15. Like you can see CAB. This is a number, not alphabets. This is a number which is written in hexadecimal. Now here is a small assignment for you. Kindly convert number 20 decimal in binary and then in octal. I'm waiting for your comments. Thank you so very much. Our next lecture will be base conversions. It will be our lecture number 3 of TLD.